So this. Okay, hopefully we got most people who were trying to join with the broken link. Thanks everyone for joining our physics colloquium. Really happy to have Abigail Vieregg today. Abby is a professor at the University of Chicago, where she's been since 2014. She works on all wavelengths of physics from all corners of the Earth, all the way from California to Antarctica to Greenland, and many other places, building things both on the ground and in balloons. And she works a lot on CMB physics, but today she's mostly going to tell us about RNO-G neutrinos. So take it away, Abby. Lovely to have you. I wish we could have you in person.
Yeah, I wish so too. That would be nice. Especially because it's like 40 degrees and raining in Chicago right now. Let me see if I can share my screen. First. Okay, can you see that? Okay, good. So yeah, I figured that, there's quite a few people at SLAC and Stanford who work on CMB and CMBS4, which is a project I've become more involved in the last few years. So I thought I would spend the time talking about something different, which is how you might go about discovering the highest energy neutrinos. So first I have to set the stage. So neutrino astronomy, I think it's kind of interesting when you boil it down. What has been done with neutrino astronomy so far? I think that's the first question. So before an experiment called IceCube came along, actually a lot happened with neutrino astronomy. So the sun was observed in the light of neutrinos, actually first by Ray Davis in his Nobel Prize winning experiment, which basically had a big vat of stuff underneath. Yeah, feel free to ask questions in the chat at any time. Yeah, which had a big vat of stuff underneath the Earth that detected electron neutrinos coming from the sun. And from that measurement, what he measured is that there's a deficit of electron neutrinos. There's many fewer, about 1/3 the number that you might expect coming from the sun compared to sort of astrophysics calculations. And this was called the solar neutrino problem for a long time. And it turned out that this was evidence of neutrino oscillations, that what had actually happened is that electron neutrinos were made in the sun, and then they oscillated to different flavors that his detector wasn't sensitive to. And then another source that's been seen in the light of neutrinos is supernova 1987A, where we got lucky basically. And 30 years ago, a supernova went off in a nearby place in the universe. And we measured neutrinos with actually a few different detectors from that event. And the spread in arrival times of those observations of the neutrinos, the spread of arrival times of the neutrinos allows you to place actually a limit on the neutrino mass and constrain neutrino decay scenarios. So I think it's interesting that actually just from looking at these two sources in the light of neutrinos, you can actually start to answer some really interesting particle physics questions. So it kind of ties together a bit of astronomy and particle physics. So the big sort of game changer in the last 10 years with regards to neutrino astronomy has been IceCube. So IceCube is an NSF funded experiment at the South Pole, where basically what they've done, and I'm not actually a part of IceCube, the thing that IceCube has done is drilled 2-mile deep holes into the Antarctic ice at the South Pole and lowered what's called photomultiplier tubes down to the bottom. So photomultiplier tubes just take single photons and amplify them so you can see them. And what they're looking for is when a neutrino interacts in the ice, it makes a particle shower that gives off Cherenkov radiation, and they're looking to see that. So what has IceCube done? So IceCube has done a few things. The first thing that IceCube did 7 years ago is they made the first detection of the astrophysical neutrino flux. So that's neutrinos that are coming from somewhere outside the Earth and its atmosphere. And on the left is just a plot versus energy. So this is number of events versus energy. and the black points are their data, and there's a bunch of background background levels that they expect in the colored histograms. And what they're seeing, especially as dominated, can you guys see my cursor? You can, right? Yeah, so especially as dominated by these points here, is they're seeing an excess above even sort of the sort of high side of the background estimates that they have. And it's even more compelling, I think, when you turn to the plot on the right and you see that the excess that they're seeing isn't just randomly distributed across the sky. It comes from directions that their telescope essentially is more sensitive to. So IceCube has successfully detected the astrophysical neutrino flux, a diffuse flux across the sky. And their sensitivity goes up to something like 10 PeV. And we're going to have to get good at our large exponents. So PeV, a peta EV, that's 10 to the 15 EV. So IceCube goes up to about 10 PeV. So IceCube not only has seen a diffuse neutrino flux, but IceCube also has maybe seen the first evidence of sort of a multi-messenger event with neutrinos. So in 2018, IceCube saw this really nice looking neutrino event on the upper right of the plot. And that's coincident in both space and time with this blazar that, as observed by both Fermi and other ground-based telescopes. And this is a correlation at about 3 sigma with a flare from this blazar. So that's kind of compelling, but it doesn't reach the sort of 5 sigma gold standard that we would like to see in the field to really be compelling. But it's certainly a very interesting event. So one thing, just as a diversion, while we're talking about sort of the science motivation, my student at the beginning of in March, when everyone was sent home. And we were all trying to figure out how to work efficiently from home. He had this idea to write a paper. So it was kind of an amazing thing. While I was, totally panicked and taking care of my kids full time, he was hacking away at his computer writing this paper. So the question you might ask is, okay, so IceCube saw, a coincidence with this flaring blazar, but can blazars like that, so blazars, are energetic sources in the universe, can they maybe be responsible for the entirety of the IceCube flux? Like, we'd like to figure out where these things come from. Where do neutrinos come from? So is it possible that sources like that one could contribute, be a big contributor to the flux? And you don't have to read this plot thoroughly, but the bottom line is, if you look at the right-hand side, the answer is no. You can set an upper limit based on combining some data from gamma ray telescopes with IceCube data that says that the upper limit on the amount of IceCube neutrinos that could be coming from sources like that one is only about 15% of the flux. So it's nice, you can look for time coincidences, but this type of source, it's not like a woohoo, we found it all, we found all the sources. It's not the full story. There has to be something else. So we're not the only ones who said something like that. Lots of people have said something like that. And a pretty compelling source, IceCube is looking for sources in their data. Not only coincidences with flaring sources, but they're looking for coincidences with sort of steady sources, right? So sources like active galactic nuclei, for example. That's black holes in the center of galaxies that are accreting mass. So, they can analyze their data, and look for excesses at certain points in the sky and try to do all the statistics correctly. And they put out a paper this year that there's, this is the most significant place on the sky right now for them. And, it's still just under 3 sigma. So, okay, they're starting to maybe see sources pop out, but again, nothing super compelling so far. But you can ask, like, this is a kind of source called an AGN. So you could ask, okay, well, can AGN make the IceCube neutrino flux? And again, you don't have to look through this plot unless you're an expert, but the bottom line is, we can go again and look at gamma ray maps of the sky and try to correlate IceCube data and ask the question, like, okay, what fraction of IceCube neutrinos could be correlated with sources like this? And the answer is actually maybe, that it's hard to put a stringent constraint on the fraction that could be coming from AGN. And I always like to say that, like, one reason why it might be hard to put a stringent constraint is that, you know, maybe there's a discovery around the corner. Maybe IceCube is actually starting to see some correlation, which they are showing, you know, and maybe this is a promising type of source for them to keep looking at. Okay, so that was just a little diversion. But the thing that I spend most of my time thinking about is how do you build a detector that goes beyond IceCube? So IceCube kind of peters out. It's not really that sensitive beyond something like 10 PeV, but there's particles above 10 PeV and we've seen them. So we've seen cosmic rays, which are charged particles, all the way out to 10 to the 20 EV. So there's all these bumps and wiggles on this plot. But the only thing you really need to know is that there's cosmic rays all the way out to 10 to the 20 EV. There are sources in the universe, and we actually don't know what they are or where they are, that are making really high energy particles. And we'd like to figure out what those are. What's the physics that drives them? And one way to do that is by looking for the neutrinos that accompany these cosmic rays. So it turns out that I think neutrinos are the best way to view the ultra high energy universe. So that's the universe well beyond what IceCube can see, but a universe that we can get some grip on by looking at the highest energy cosmic rays. But cosmic rays have their limitations, right? They're charged particles, which means that they get bent in magnetic fields, and it's really hard to point them back to their source. So, you know, ideally, if what you want to do is make a map of the sky, you want an uncharged particle because, you know, the galaxy has magnetic fields and it's hard to, you know, figure out what that transfer function is to map that back onto the sources for charged particles. So, you know, that leaves you with photons, I guess. That's what most astronomers use, is a variety of different kinds of photons. But again, if you want to look at the really high energy universe, photons actually interact on their way here. From outside, you know, from far away, above a certain energy, because they pair produce on the cosmic microwave background and on other, you know, other light that's created. So basically we're stuck with neutrinos, which I say it that way because I would love it if there was another way to do this, because building detectors that look for neutrinos, it's hard. I mean, the same thing that makes neutrinos a really nice messenger particle makes them a really hard particle to detect. They don't interact very often. That means they travel really far through the universe. You can look far away at the high energy universe, but it's just really hard to build a detector to see them. So here's just another way of looking at what I just said, which is if you make a plot of energy sort of across all energy scales from sort of the lowest, you know, let's say like Big Bang neutrinos energy all the way up to, you know, the highest energy particles that we've seen at about 10 to the 20 EV. And you put that on the x-axis, and then you put distance, you know, farther and farther away from Earth on the y-axis. There's actually this interesting region of phase space that's dominated by a few different physical processes that you really can only see with, I suppose, either gravitational waves or neutrinos. You can't see that upper right-hand corner with photons or cosmic rays. And so if we want to make the most energy, you know, observations of distant sources at extremely high energies, we're sort of stuck. We're stuck with neutrinos and maybe gravitational waves. Okay, so how are neutrinos made? So it sounds great. We could have these great messengers and look at, you know, really far away things and do cosmology with, you know, measuring sort of what's the evolution of high energy sources in the universe. That would be great. So the first thing we need is a production mechanism for neutrinos. So one way that neutrinos are made at the highest energies is actually by direct production from cosmic rays traveling through the universe. So cosmic rays are charged particles, and if it's a proton, then eventually it'll interact with the cosmic microwave background photon, which are everywhere in the universe, go through what's called a delta resonance, and then eventually decay into neutrinos. So I think about this kind of like the way you might make a neutrino beam at Fermilab, where you have a charged particle, you slam it into a target. In this case, our target is the CMB, and then out the other side comes a neutrino beam. Okay, so the problem with neutrino astronomy, right? It's all great. I would, you know, it'd be great, and neutrinos are a really nice messenger for learning about these sources, but the problem is they don't interact very often. So it's really hard to make a detector. So what IceCube has done is made a really big detector. So you need a huge detector to have a chance to even see these really pretty rare particles that don't interact very often. They only interact via the weak force. And the weak force, of course, is aptly named, right? The cross section is just tiny. So it's even worse than that, because if you want to push the energy threshold higher, if you want to see even neutrinos that are even higher energy, those neutrinos are even more rare, right? Because everybody, anybody who's studied astronomy knows that everything's a falling spectrum, right? Like the higher energy you go, there's just less stuff because it's harder to accelerate things to that energy. So you need an even bigger detector. So, you could build 100 ice cubes, I guess, but, I would argue that what you'd have to do is get creative. So eventually you sort of run out of steam and you can't build a bigger ice cube to detect higher energy particles. And that's really the fun part. So how do you do that? So there's at least two ways. There's two ways that we're pursuing. One is, instead of looking at optical emission, where the neutrino interacts in the ice and gives off optical light that you look for, that's what IceCube does. Instead of doing that, what you do is you look for radio emission, actually. So if a neutrino interacts in the ice and makes a particle shower, that particle shower actually emits Cherenkov radiation, which is broadband. And if the wavelength that you're looking at, so the radio waves we're interested in, the wavelength is, I don't know, let's say it's a meter. If the wavelength that you're looking at is bigger than the size of the shower, you get a coherence effect, which is, I think my favorite trick in physics is coherence, where if you have a shower that's smaller than, this example, you have a shower that's smaller than the size of your wavelength, then all the sine waves of that radio emission add in phase. They add coherently, and you get this boost where the power that you see goes like the energy of the shower squared. Whereas for optical, it goes like the energy of the shower. Okay, so why do I tell you that? I tell you that because what it means is, for really high energy showers, remember, we're looking for super high energy showers, the power emitted in radio is actually stronger than the power emitted in optical. So you could build a really big optical detector, but there's actually more power to look at in radio. And this plot on the lower right is actually a plot that we made when I was in graduate school. We took a big set of radio antennas up to end station A in SLAC and slammed a bunch of electrons into a target of ice, and we looked for their radio emission. And this is what it looks like. You can kind of think of this plot as like an oscilloscope, where you have the x-axis is time and the y-axis is, well, in this case, it's electric field, but it's sort of like an oscilloscope. And the pulse that we see from these showers is a really fast impulse. It's less than a nanosecond long. So what that means, if you can do Fourier transforms in your head, which I know some of you probably can, really fast things correspond to really broadband things. So what we need to do is build a detector that's sensitive to really, really broadband signals and really fast impulses in radio. There's actually another method that you could look for radio emission from neutrinos as well, and that's through this channel. And this channel actually, people really only started thinking about this 7 or 8 years ago. It only became popular at that time, and it's kind of taken off, I'll say, in the last few years. So the other way you might detect radio emission related to neutrinos is if a tau neutrino interacts in the Earth. About half the time it makes a tau lepton. So a charge current interaction gives you a tau lepton. And then these things are so energetic that the tau is so forward boosted, to use the particle physics words. It's so boosted that it travels about 1 kilometer before it decays. So that means that it has a real chance of escaping the Earth, making an air shower, and then you actually can get radio emission from that air shower, because the particles in that shower are sitting in the Earth's magnetic field, and that makes synchrotron emission. So this is sort of the second way you might do it. So you can imagine, like, if you put an antenna high up on a mountain, for example, you could look for this signature coming up. So we have actually a few different handles on ways to look for radio emission from high energy neutrinos. Okay, so I'm going to focus mostly on this, this Iscarian, or the first method I talked about. It's called the Iscarian emission, named after the person who thought of it. So we can do a back of the envelope calculation and say like, okay, well, the theorists are telling us, and we can sort of extrapolate from what IceCube has seen also, that there should be about like 1 neutrino at these really high energies per square kilometer per year. And that's a really small number. So that's a bit discouraging. And it's, you know, worse than that because the interaction length of these neutrinos is about 300 kilometers. So that sounds really long. It takes on average about that long before it interacts. But actually for neutrinos, that's pretty short, right? That means that for these high energy neutrinos, any neutrinos that are coming up through the Earth actually get absorbed, right? Because it's so high energy that the cross section's high enough that they get absorbed in the Earth. Anyway, but what you need is a huge, at least 100 cubic kilometers radio transparent detector. And I'm not going to build that in a lab. So that means we have to look for naturally occurring, you know, large chunk of radio transparent dielectric. And it turns out that after we've measured a variety of places, it turns out that Antarctica and Greenland, these sort of big sheets of ice, are the best place to do this. So there's sort of 2 ways that you might do this. One is by flying a balloon over Antarctica. There's a long duration balloon program run by NASA where you can fly a balloon over Antarctica and actually look down at the ice for radio emission from neutrinos coming up at you. And then the other thing you might do is basically put a bunch of radio antennas in the ice and see what you get. So you'd put a bunch of radio antennas spread across the ice, maybe down shallow holes to get away from surface effects, and see what you get. So those are sort of the 2 concepts that I'll talk about. So the first is the balloon concept, and I'll talk about that first because really it came first actually. So Anita was designed for really high energies, right? The 2 ideas, let me go back a slide. The 2 ideas have different pluses and minuses, right? The balloon concept, you can see a lot of ice, like the horizon is 700 kilometers in every direction when you're up on this balloon. So you get a huge volume to monitor. But the downside is that you're pretty far away from the events. So that means that the energy of those particles has to be really high for you to see them. So what that translates to for Anita is that Anita really is only sensitive at the very upper end of where we're interested in. It's sort of 10 to the 19 and above EV. So just at the upper end where we think, you know, where the cosmic rays become more and more rare. So this is a picture of Anita and the team that was on the ice a few years ago to launch one of the flights of Anita. So Anita has actually had 4 flights thus far. And Anita is just a bunch of antennas, you know, that are basically make an interferometer. So you put a bunch of antennas on a payload, you fly it over Antarctica, and then you use the time delays between the antennas to try to point back where your radio signals are coming from. And then you use physics to figure out what that means about the neutrino directions. So here's just a schematic of how Anita works. So here's that Iscarian channel where you have a neutrino, it makes a shower, you get this Cherenkov radiation and you see it from the balloon. And the signals, you know, a signal, if you saw it like this, it would be vertically polarized. So the electric field that you see, this is actually pretty important. So the electric field that you see would look vertically polarized. And that's just because of geometry. You tend to see the top of the cone, which, because the Cherenkov cone is radially polarized, you tend to see signals that are vertically polarized from the balloon. So that's one of the cuts we're going to use in analysis, is like measure the polarization of the signal, and it's got to be sort of vertically polarized to be an Iscarian neutrino. And then it turns out that this tau neutrino channel, that was sort of the second method I talked about of detecting these things. The tau neutrino channel, it actually makes horizontally polarized signals in Antarctica. And that has to do with, you know, the direction of the Earth's magnetic field and how the radio emission is made in the air shower. So it's actually kind of nice. We can discriminate the 2 channels. We can say if it's vertically polarized, you know, put it in this channel with the Iscarian, you know, to look for Iscarian signals. And then you can, you know, have a different channel that looks for these tau neutrino signals. So someone asked, rather than a balloon far away from the ice, what about drones or a modified plane? Yeah, so you could do that. And in fact, it would be a little bit better because the balloon flies per unit time, it would be a little better. So the balloon flies at 40 kilometers, but like the optimal height would be something like 10 kilometers because the balloon's a little bit too far away to be optimal. There's a few problems with a drone or a plane. One is that they tend to make RF noise. So you'd have to have an instrument that was like really RF isolated, because what we're basically building is a super sensitive RF detector. So we have not done it because we think that the background from the plane itself would just swamp you. Also, you'd have a live time issue where like one balloon flight gets you 30 days and you'd have to have many, many flights like that. Okay, so that's the tau neutrino channel. And then actually what Anita sees a lot of are cosmic rays. And Anita sees cosmic rays like this. So it sees cosmic rays in either two ways. One is, you know, cosmic ray just makes a shower and you see the signal. But actually more often, because Anita is actually above most of the atmosphere, more often what you get is a cosmic ray comes down, makes the particle shower, and then the radio emission actually bounces off the ice and back up to us. And we can tell this because when it bounces off the ice, the Fresnel coefficients tell you that the electric field has to flip. And we actually see that in the data. So you can see that when you look through the data, cosmic rays that have this geometry look not flipped, and cosmic rays that have this geometry look flipped. So it's actually kind of nice. We kind of know what we're looking at. So we can run an Iscarian search, a search for emission from neutrinos in the ice. And we've done this with all 4 flights of Anita. And actually each time we basically see something like 1 on a background of 1, which I like to say means that we're really good at estimating our background, because I like to put a positive spin on a non-discovery. But this is a non-discovery, right? But the thing that's kind of nice is that we've at this point honed in our Monte Carlos, our simulations, so that we can make a nice simulated event and compare that to the candidate events that are left after we sift through the data and apply all our cuts. And it looks pretty similar. So it's good. We don't think there's a mistake. We just think that this is probably background. So that's the in-ice neutrino detection. Now, Anita has seen a bunch of cosmic rays, something like, 70 cosmic rays over the course of 4 flights. That's fine. I mean, these are really high energy cosmic rays. It's kind of nice. Our instantaneous volume is better than Auger, but we don't have very much live time. So, experiments like Auger do much better than us in this regard. But the thing that's interesting, or at least, makes you scratch your head, is that I talked a little bit about when the cosmic ray signals bounce off the ice, you get this flip in polarity. And so if you think about it, that tau neutrino channel, it would kind of look like a cosmic ray signal bouncing off the ice, except it wouldn't be flipped. So you might be able to tell, like, you'd have this bunch of cosmic rays coming and they're all flipped in polarity. But if you had events that were coming up that weren't flipped, then those wouldn't be cosmic rays, but those would look like those sort of tau neutrino channel. So it turns out that we saw a few events that looked like this throughout the flights of Anita. And this has actually gotten sort of some attention from theorists, and eventually it got the attention of the press because somebody, somebody not us in the collaboration, talked to some news, how this goes, talked to some news article about, Anita discovers, beyond the standard model physics, which I'll get to. But basically what we saw in the Anita 1 and 3, the first and third flight, is that we saw in each flight one event, which we call mystery events because we don't know what they are, that looks like a typical cosmic ray event. This is on the left, but it's exactly inverted. So you can see like the signal looks pretty similar. And this is after, of course, all the cuts to sift through the data. And the background for this is pretty small. And the reason the background is so much smaller for this is because we have a few more handles to cut out background than we do for the in-ice neutrino channel. We know a little bit more about how radio emission from air showers works. So, that's kind of interesting. So you ask yourself, okay, so could those be tau neutrino events? Why not? Well, the problem is that they're really steeply upgoing. So they come from like 35 degrees below the horizontal, which I said much earlier that neutrinos at these high energies should be absorbed in the Earth. So what that means is, like, if you saw a couple of events at 30 degrees coming up, you'd expect a lot more that are skimming towards your detector. Like it just doesn't work that way. If you saw one coming up, you expect a lot more skimming, unless you got the energy wrong or you got the cross section wrong, which I suppose is possible. So the events are too steeply upgoing to sort of nicely fit everything. And of course, this prompted a bunch of papers. Maybe there's some more mundane answer, like maybe there's some non-physics background that we haven't accounted for yet, but we don't really know what's going on. And then it got worse in Anita 4. So in Anita 4, we just put out this paper. We were sort of sitting on this data for like a year maybe, because we didn't quite know what to do with it. So Anita 4 saw a handful, namely 4, polarity flipped events, and this time it's near the horizon. And I shake my head because I still don't know what to do with this. And we spent a long time doing simulations to try to estimate the background, and we basically have no idea what's going on, is the short answer. We have this sort of population near the horizon and a few steeply upgoing events, and they really do look like cosmic ray events, but not inverted, and we don't really know what's going on. Okay, so that's unsatisfying. But what we'd like to do, because I'm an experimentalist and you have a mystery like that where you don't know what's going on. Maybe it's some background that we don't understand. Maybe it's cosmic rays that do weird things when they, bounce off the ice and it just looks not inverted. But one thing that you can do is build a better detector. So you can build a better detector to try to not only figure out what the heck is going on with all those sort of cosmic ray-like events that could be hints of other things, but also to just do a better job on the Iscarian channel that Anita was built for, and go out and find those ultra high energy neutrinos through that channel that we think we understand really well. So this is a proposal that we actually just submitted to NASA through a new call called the Pioneers, which we're calling PUEO, the Payload for Ultra High Energy Observations. We picked the name PUEO because the University of Hawaii is sort of has been the lead institution on Anita for a very long time. And they wanted a name, and they picked PUEO, which is this really cute Hawaiian owl up on the right-hand side. Okay, so here's the sensitivity projections on the left. So here's the combined Anita 1 through 4 limit in pink. So that's, you take all 4 flights of Anita, you combine it, that's what you get. And actually, with some technology advances that have come along in the last 10 years, we think with 1 flight of PUEO, we can get here. That's this black line. That's about an order of magnitude better than all 4 flights combined. And if we had 3 flights of PUEO, we could get down even farther. And the thing that's interesting is that, like, as you can see from this plot, Anita sort of misses the mark, frankly. I mean, Anita is, kind of not quite sensitive to really rule out sort of the next round of models or see something. It's, at this point, it's pretty unlikely if we flew Anita again that we would see something. But the technology advances that have happened for PUEO allow us to really change the game at the highest energies. So how did we do this? So the other thing that's nice is, a balloon experiment like this has especially large volume for point sources and multi-messenger searches, which is kind of nice. So how do we do this? So we did this by redesigning the trigger of the experiment. So I said before that this is basically a radio interferometer. So we have a bunch of antennas that, you measure signals and then you cross-correlate them. But instead of doing them in analysis, we're just going to do them, at the trigger. Why not? Now there's FPGAs that can do this in real time. So we're just going to figure out for a plane wave coming into the payload, what should the time delays be? And we're going to line up all the antennas at the trigger level and do what's called beamforming. So we'll do that with some new boards called RF socks, which everyone is using these days. And so that's how we got those improvements over Anita. It's just by redesigning the system enabled by new technology. Okay, so we're also working hard on pushing forward on the ground, not just getting those highest energies from a balloon. And working from the ground has some major advantages. You can run your experiment longer, you're closer to the events, you understand your backgrounds better, but at the same time, you have a smaller volume you can instrument. You can't look at 700 kilometers in every direction all at once. So there's an existing experiment called ARA at the South Pole. It's a bunch of antennas that are, put just below the surface of the ice at the South Pole. And right now, ARA has 1, 2, 3, 4, 5 stations sort of put out at the South Pole, stretching out and away from IceCube. And those stations are all running and running well. A few years ago, we implemented this phased array trigger technology on ARA also, that we are going to put on this new PUEO payload. And what we managed to do in the field, and this is a plot on the left for the real hardware nerds. So what we managed to do in the field for real is this is a plot of trigger efficiency. So as a function of signal to noise ratio. So what we've done is taken the old ARA trigger here. So this is what the experiment was doing. And we just, by changing the logic of what was happening, we got basically a factor of 2 improvement on the trigger. So that's, no more hardware, just different logic of what's happening in the background. So I thought I'd show just a few pictures of South Pole. Here's a picture of us deploying some antennas. These are different kinds of antennas down the holes. And I really like this because it really makes the experiment look kind of like it should. It's a little bit technology and a little bit arts and crafts and a lot of shoveling snow, where you, at the end of the day, what you have is like a plywood box and some insulation from Home Depot, and you stick it out on the Antarctic plateau with some fancy electronics inside and just let it sit all winter. And at the end of the day, it just looks like a plywood box sitting on the ice. So ARA has been running for a while, and finally we've sort of reached this equilibrium where the new hardware that we've deployed is working really well. And all 5 stations are running, and ARA, the data that's already in the can will start to be, pushing into models of neutrino production in the next few years. So I think it's worth talking a little bit about what's coming down the line for ground-based experiments as well. So that's IceCube Gen2 actually. So IceCube, I've said, is this optical detector, but the next generation of IceCube, the plans that are formulating right now, will have not just an optical component, but it'll have a large radio component as well. And that's because IceCube has seen the value of extending to the highest energies using this radio technique. So it'll be this nice marriage of optical and radio. And when you combine them together, you really get this nice powerhouse. So I like to look at this plot on the lower right, actually. It shows what happens if you have the optical only. And then you add this little radio extension, which is frankly a small fraction of the cost of IceCube Gen2, and you really boost the sensitivity at the highest energies. And this plot on the upper right shows flux limits as a function of energy. And we sort of hope to get down here with IceCube Gen2 well into the region where we should detect the extension of IceCube's neutrino spectrum out to the highest energies. So there's actually a reference design for Gen2 that looks a lot like ARA, and it looks a lot like an experiment that we're currently working on to deploy to Greenland. And it's a bunch of antennas down holes and some antennas at the surface, and you use this phased array trigger to optimize your sensitivity, and you look for radio emission from neutrinos in the ice. So the sort of middle ground between ARA, which is currently running with 5 stations at the South Pole, and Gen2, which hasn't even been proposed yet, is an experiment called RNO-G, the Radio Neutrino Observatory in Greenland. And this is really, I would say, paving the way for IceCube Gen2. So there's a lot of, to go from 5 stations to something like hundreds that Gen2 is hoping to build at South Pole, you have to have some sort of middle ground. You have to test tens of stations, and you have to really design your stations with the idea of scaling up in mind. And at the same time, you might as well discover ultra high energy neutrinos. At least that's the way I see it. So the Europeans actually found funding for this. So we are starting this year. We were supposed to deploy last June, but it got delayed to this year. Our first 10 stations are actually sitting in the lab here in Chicago, and they're going to go out the door, we hope, unless there's further delays from COVID, in 2021. So the idea is that we'll use this not only to build sort of that mid-scale experiment that'll get the sensitivity, to maybe discover neutrinos at the highest energies, but also be that sort of thing that allows us to scale up to Gen2. And you'll notice right away, the reference design for Gen2 is the design for this Greenland experiment. And that's not a mistake. That's because, we think that the design will be portable to the highest energy, portable to the largest scales. And then I like to show pictures of, some electronics boards. We basically have designed every board anew with this experiment to try to optimize power consumption, noise, reliability, cost, so that we can scale up to the size of IceCube Gen2. And then I thought I'd just show some pictures of all the antennas that are floating around in my lab. I went in and took this picture today of all the antennas that are floating around right now. And my students are working hard to design and test many pieces of this project. Okay, so I think I'll leave it there. And I'll leave you with this plot that, you know, is kind of my hope for the future, at least from the ground-based side, which is, you know, we'll have this mid-scale experiment that's already sitting in the lab here and is planned to go up in 2021 to Greenland. And then that'll allow us to leapfrog to a very large component of IceCube Gen2 that'll have the sensitivity of something like this down here at the bottom of the plot.
Awesome. Thank you so much, Abby. We can clap virtually. Exciting future. Let me encourage students to feel free to ask questions. But I'll start with a question from Maria, who asked about midway through your talk. Maria, do you want to go ahead?
Hi, but I think Abby already replied.
Yeah, I answered it during the talk.
Yeah.
Oh, okay. Sorry.
Okay.
Yeah.
Perfect.
So, Yannicka, is that
Okay.
how you say your name?
Yeah, go
Yeah,
ahead.
she asked, why, can I explain why the taus are typically horizontally polarized? This is when I would go to my whiteboard, which I actually have behind me. But so the radio emission from the air showers, okay, radio emission from air showers in general in Antarctica is horizontally polarized. It's not just the tau channel, it's any particle that makes it a shower in the atmosphere. So why is that true? So a particle shower, the way the radio emission is made is from synchrotron emission. So you make a bunch of electrons and positrons, and those electrons and positrons split around the magnetic field lines. So they split around the Earth's magnetic field. So it's just a coincidence, actually. The Earth's magnetic field in Antarctica happens to be mostly vertical because it's near the magnetic South Pole. And so when you do QV cross B, you get, like, if you can imagine looking down the axis of the shower, you get, you know, in a vertical magnetic field, you get the particles splitting this way, which means the electric field is that way too. So that's how you get horizontal in Antarctica.
Awesome. More questions? Feel free to raise your hand or put it in the chat. Roger, did you have a question?
Yes, thanks. Very, very nice talk, very exciting prospects. Could you say a little bit about the prospects are for improving the facilities for the ultra high energy cosmic rays using RNO-G and so on? I'm thinking about the prognosis for things like GEM-USO and so on. What's going on there?
Yeah, so I don't know of plans. I mean, maybe you know of plans, but I don't know of plans to like expand the ground-based sort of Auger-like detectors enormously. But I do know, as you said, there's hopes to go into space, right? So Angela is working on, you know, a proposal called PUEO, which would look for ultra high energy cosmic rays and neutrinos, and GEM-USO. I don't know what the status, sort of the official NASA status is of those.
Yeah, she gave us a talk about it just over a year ago on that. Yeah. Yeah.
I know there was, you know, funding. There was sort of development funding given to those projects, but I don't know beyond that.
Well, a very quick question. Is your site in Greenland the same one that people working with the Event Horizon Telescope hope to deploy at?
Yes. Yeah, so I actually have talked to them in the last few weeks that, yeah, anyway, about shared resources, but yes.
Great.
Okay, we had a question about the cost per detected neutrino.
Right now it's infinite. Is that too snarky of an answer? No, right now it's infinite. Okay, so how to even attempt to answer that question? I would say that, so let's say that the IceCube neutrino, let's just start there. Say that the IceCube neutrino spectrum just continues, you know, at whatever power law they've measured and just continues. We actually should see that, with something like IceCube Gen2, you expect to see that plus any cosmogenic neutrinos you might see. They're actually two separate populations. So let's say IceCube Gen2 realistically should see, 50 neutrinos maybe. Maybe I'll get lucky. Maybe it's only 10 at the highest energies. So it's a lot. What's the cost per neutrino? $1 million. That's a lot. Okay. Cindy asks, if you're doing cross correlation on the FPGA, is that fast enough that there's a good enough downlink to the ground that you can do live follow-up alerts? That's a great question. It's something we think about a lot. The answer is no, we can't, like from the balloon and even from South Pole, the connection from pole, we can't, the data rate, it samples, so the instrument is constantly digitizing at Nyquist, which is, it's like 2.6 gigasamples per second. It's really fast. It's a lot of data. So we have to downsample, we have to trigger. We have talked about trying to loosen the trigger restrictions, right? So that like, if we get an alert from somebody else, we could quickly, we could loosen our trigger restrictions in a certain direction, right? And try to be more sensitive to that direction. But issuing alerts, so we could do live follow-up like that, right? Where we could receive an alert, change our trigger and change the way we're looking. But in terms of like issuing alerts, we have to trigger and down select, of course, and then issue a small, we can only look at a small fraction of the data.
Okay, we have a question from Vahe.
Well, actually, she just answered the question. But I make one comment, since you're talking about this discoverer of this radio effect. The proper pronunciation of the name is Iscarian.
Yeah, I guess we all anglicize it and everyone says Iscarian, but Iscarian, yeah. Thanks.
All right, we have maybe time for one more question. Is there another question?
See, I have one, but I can't raise my hand as a co-host.
Go for it, Leo.
I didn't really understand the sign of the radio pulses. You had a plus and minus. And if I had thought of that as an optical pulse, I would say, well, I could invert that if the pulse propagated through a dispersive media. So the sign could be dependent upon how far it propagated. And so I'd like to understand the sign of that better.
I'm trying to think about what you're talking about. Are you talking about?
So you showed some, it goes up and down and up, and then it's inverted in a different case.
Right.
And what is it that determines the plus sign? And how do you know it's not dispersive propagation, that the group velocity and the phase velocity are different?
Yeah, so that's a really, so you mean you're trying to think of things that could mimic inversion.
Right.
Right. Yeah. So that's a really good question. So you could, right? If you had, that's exactly right. So if you had, and I didn't talk about it, but there's maybe other ways to, I sort of said like, well, maybe there's some background we don't know about, but or we haven't yet calculated, but one of the possibilities is like, is there some way that if you're living in, if we think that the signals are being dispersed exactly as you say, or if let's imagine the surface of Antarctica is rough, right? At the scale of a wavelength. Then when you have the radio emission bounce off of it, you could totally imagine that it messes up all the phases, right? And so then you might end up with something that looks inverted. I started a graduate student 2 years ago on a project to simulate exactly that, to take an FDTD, a finite difference time domain simulation, and actually do Maxwell's equations and see if we could take like this pulse and bounce it off, put it through dispersive media, bounce it off of rough surfaces and see if we could like mimic this flipping. Because that's the thing that I thought was most likely to be happening, because this is not like a lab controlled experiment. This is Antarctica where there's stuff everywhere. It turns out, at least what we found, is that it was hard to get it to, so in order to see signals that look that well flipped, we think we should have also seen a bunch of signals that kind of look in between. You know?
Yeah, that makes sense. Yeah.
Yeah, and we didn't see that. So we were sort of, that was where that simulation project ended, was like, well, we're sort of seeing this distribution and really our data is only at this tail. You know, so what's going on? But yeah, that's exactly right. That's where my brain went too.
Thanks.
All right. Thank you. Are there any other burning questions? Well, let's thank Abby again. Sorry we can't take you out to dinner and see you in person, but thank you so much for joining us.
Thanks for coming. Oh, there's one more question.
Oh, one more question. Yeah, you want to go ahead?
Oh, someone asked, just sort of getting back to the most important questions. What can you get from high energy neutrinos that low energy ones can't tell you? Okay, so I'm trying to put high and low in context first. So there's actually neutrinos across like a super wide range of energies. But what can we learn from the highest energies that we didn't already learn from IceCube? That's maybe one question. So I didn't go into it, but there's actually kind of two populations of neutrinos that we think are there. One is the population that IceCube has seen, and that's direct, we think, direct production from astrophysical sources. And then there's a second population of these neutrinos that are made from cosmic ray propagation through the universe. So that is these really high energy GZK neutrinos. So what do we learn if we see those? I think that's one question you could ask. Like, what do we learn if we see these really high energy GZK neutrinos? And I think IceCube could see them, but it's maybe unlikely. So what do we get? We get another handle on cosmic ray composition, actually. We get a handle on source evolution. So how do the highest energy accelerators evolve as a function of time or redshift? There's also particle physics things we get. So you could measure like the neutrino cross section at energies much higher than the LHC. So if you do sort of the center of mass energy transformation to be the equivalent of like a collider, these energies are a factor of 10 higher in center of mass energy than the LHC. So you can get neutrino cross sections. If you could measure the flavor of these neutrinos, you could place bounds on neutrino oscillations actually over really long distances. You could do Lorentz invariance violations, the list goes on. So there's a variety of sort of from both angles, the particle physics angle, that really getting to the highest energies gives you a longer lever arm on the physics. That's, I guess, how I think about it.
Awesome. Thank you. That was a great question, and I think all of us learned something from the answer. So thank you so much, Abby.
I know, and different people would give you a different answer too, right? Like I just give you my list of the top 5, but like someone else would give a different,
great.
top 5.
Super fun. All right. Thanks everyone for joining us, and thanks again to Abby.
Thanks.